All right, good afternoon, everyone, and welcome to today's USACM Student Chapter Seminar. Today, we're delighted to have Dr. George Pasparakis from Johns Hopkins University, who will present his work on joint spacetime wind-field data exploration using sparse representations and non-parametric Bayesian dictionary learning. Dr. Pasparakis is a postdoctoral research fellow at the Hopkins Extreme Materials Institute at Johns Hopkins University, where he works in both Shields Uncertainty Quantification Group and Graham Brady Research Group. He earned his PhD in civil engineering with highest honors from Leibniz University Hannover in Germany, where his work was supported by the Mercury Actions Fellowship. He also holds a diploma in mechanical engineering from the University of Thessaloniki in Greece. His research interests focus on stochastic dynamics, uncertainty quantification, Bayesian neural networks, computational mechanics, and advanced signal processing. He has made significant contributions to solving complex engineering problems, particularly in areas such as vibration energy harvesting, wind-field reconstruction and extrapolation, and uncertainty quantification in materials modeling under extreme conditions. Please join me in welcoming George Pasparakis. George, the floor is yours.
Hi, everyone. So as the title suggests, actually, first of all, let me thank all of you for the introduction. As the title suggests, today I'm going to present my work on joint space-time and time wind-field data extrapolation using sparse representations and non-parametric Bayesian dictionary learning. This has been the result of my PhD work together with my postdoc, and it's been the result of the collaboration of me, Professor Kuyumzoğlu, and Professor Shields. So this talk today is about the stochastic simulation techniques and inverse problems pertaining to wind field statistics. And basically, it demonstrates the feasibility and the variety of techniques for reconstructing stochastic field statistics through a variety of methods encompassing sparse representations. So moving to the outline of my presentation, first of all, I will present a little bit about the wind field modeling motivation and how this is viewed both from a simulation and an instrumentation point of view in stochastic mechanics and structural health monitoring. Then I will present shortly the stochastic simulation technique we have used in terms of simulating appropriate stochastic processes and stochastic fields. Then I will present elements of sparse representations, and in particular, compressive sampling and matrix completion, which both are related. And then I will introduce an advanced signal processing technique relating to non-parametric Bayesian dictionary learning. Through all of this, I will also present some results through all of these sections. And then I will move on to the application of non-parametric Bayesian dictionary learning for wind field extrapolation in both 2D and time in simulated data, and then also some experiments for boundary layer wind tunnel testing. Okay. So in general, as an overview, in wind engineering, the wind loads are the governing design loads for several structures, such as for slender buildings and long bridges, which are typically lightly damped and sensitive to aerodynamic loading. And in general, the wind exhibits not only temporal, but also considerable spatial fluctuations and variability, especially when considering modern structures that span pretty large domains. In general, a large body of work has focused on frequency domain approaches for deriving input-output relationships in terms of power spectral densities, but this has been quite limited for linear structures, whereas for structures which exhibit nonlinearity, such as example large deformations and geometric nonlinearities, a time domain analysis is needed. So this requires the simulation or the reconstruction of time histories in the time domain in the structural analysis design cycle. Here I will outline a few of the methods that are used for reconstructing wind fields or in generally flow. One of the most common one and the most standard is computational fluid dynamics approach for turbulent flow prediction, which relies on the Reynolds average Navier-Stokes equation, which typically is pretty well documented, but typically suffers from parametric or model error forms. These are typically calibrated using data simulation techniques, which minimize the error between the target flow and the partially measured flow field. And also it can be domain specific and might require recalibration to the change of input boundary effects. In practice, wind velocities and pressures are often assessed, and their interaction with structures are assessed through boundary layer wind tunnel experiments and testing through field instrumentation. And these tools have become the standard for investigating turbulent spectra, mean velocity profiles, wind effects on structures, and so on. And although these approaches offer high fidelity experimental data, which are more reliable compared to computational fluid dynamics, these tend to be, as anticipated, quite expensive, and deploying a large number of sensors, as is necessary in structural health monitoring applications, can be cost prohibitive or even cumbersome in many cases. Indicatively, some other more data-driven approaches which are quite popular. Gaussian process is one alternative, which has exhibited pretty broad applicability, especially kriging, for instance. Despite the fact that this is quite popular, it has been constrained to relatively large domains and has some limiting assumptions regarding the stationarity and the isotropy of the associated fields. And it's relying on the appropriate choice of kernels and hyperparameters. Also, within the context of very high dimensional data, the associated inversions of the maximum likelihood estimation matrices which are involved can be very cumbersome. Also, the very popular neural network applications, which are as demonstrated recently, very powerful, they might struggle with interpretability and lack of robustness when extrapolating beyond training data regimes. Also, these are very data-hungry methods. In general, it's not often the case that we will have this richness of data as needed. So, to circumvent these limitations, and in general, the research community over the years has resorted to the standard stochastic simulation techniques. These are semi-empirical methods which simulate the wind pressure or wind velocity as a stochastic field in both space and time, or as a stochastic vector process. And there has been a big body of work regarding the simulation of stochastic processes for a variety of cases, such as homogeneous, non-homogeneous, multivariate, Gaussian, no Gaussian, and so on. So the typical design analysis procedure relates to the acquisition of wind speed records, which are utilized and pre-processed to either calibrate or inform statistical estimates, which are then used through the spectral representation method to determine the response of the structure. And then this cycle is performed multiple times to optimize the designs. So what we're going to be focusing today is this part, specifically the signal processing part. And we're going to be looking at this problem from two perspectives, both from a forward simulation procedure, and I'm going to explain shortly how this is achieved, but also from an inverse modeling perspective, where we're trying to reconstruct either these simulated time histories or actually actual data from measurements. So the standard approach within the context of the spectral representation method models the wind field as a discrete stochastic vector process in space and time. For example, for a one-dimensional domain, here we have the parameterized stochastic process of the wind field in time at each location index. And the method here relies on a spectral decomposition on the cross-parallel spectral density, actually, of these pairs of points. So we have an expression for this PSD for each of these pairs of points. So this is noted by I and J. It's not included here. And by adopting some decomposition of the spectral density, such as with Cholesky factorization or something similar, one can obtain an expression here, which is nothing more than a double summation of the spatial indices in terms of the energy of this spectrum or the power of the spectrum, the frequency discretization, the frequency component here and the time, a random phase angle, which this induces the randomness in the stochastic realization, and this parameter theta, which is given in terms of the decomposed power spectrum. And this has been extended and improved over the past few decades in many cases. But the main issue of this method is the fact that as this number of points increases, first of all, there is a very high incurred computational cost because this has to be decomposed at a very large number of points, pairs of points. And also when these points become arbitrarily correlated, there are singularities of the matrix, which leads to numerical instabilities. But this all requires the knowledge of a prescribed spectrum. This is the main idea. An alternative, more efficient and recently introduced formulation relies on the fact that we can rewrite this spectral density expression, but now using a prescribed PSD as given here, multiplied by an exponential coherence function. These are, of course, design choices in terms of simulation. And this exponential coherence function typically yields the spatial characteristics of the wind field in terms of a spatial lag. So this is the spatial difference of the wind field between two different points. And by using this expression here and taking the Fourier transform of this with respect to the spatial lag, we can actually obtain a wave number frequency formulation of this spectrum. This was introduced by Benovitz and Deodatis a few years ago. And actually, this can be directly implemented and demonstrated to be applicable to the formula shown before, where again, we have a double summation now again, with the power spectral density and its discretization, now in terms of wave number and frequency components. Again, phi here is the random component that it induces the randomness is associated with that. The important thing here is that we can simulate a very large number of points, which can be arbitrarily correlated, and we don't have to perform these Cholesky factorizations. Also, from the case that we're going to study here, we can have analytical statistical estimates to compare with the actually reconstructed vectors. So we can have analytical expressions for the power spectral density, the cross correlation, the cross power spectral density, and the coherence. So we can perform a vis-a-vis analysis between the reconstructed counterparts and these analytical expressions. So effectively, what this looks like is using this formula, which can be generalized to higher domains. This is for 1D plus time. We can have simulation of time histories along the height, let's say, of a building or of a wind turbine and so on. Okay, so now we've talked so far about the simulation procedure. In general, we would like to see this problem as an inverse modeling problem, where some of these time histories are either partially observed or the whole time time history is missing. And this is a pervasive problem, not only in terms of simulation, but also in terms of instrumentation and in all of the other cases that are presented in the introduction. So all of these cases constitute a problem, which is an inverse problem. This is how it's treated in the literature in terms of both space and time. And there is significantly practical interest in actually performing these reconstructions together with associated reliable statistics. And in the literature, conventional signal processing methods have aimed at solving these types of problems through an inverse modeling perspective, but they have been quite limited and constrained by this Shannon-Nyquist sampling rate, which dictates that the exact signal reconstruction can be achieved when the sampling frequency is at least twice the highest frequency in the signal. Also, they're not very straightforward to implement in irregular sampling scenarios, and in general, they fall short when the system of equations is highly underdetermined. So when we have much more unknowns than data. So the emerging field of compressive sampling, which has emerged the past 20 years, has actually challenged regular assumptions and actually relies on the fact that signals are compressible or sparse in some domain. And this assumption facilitates the solution of highly underdetermined system of equations. So a few words on compressive sampling. There's a large number of guarantees. I'm just going to outline it here very briefly. The main assumption is that we have a signal which has a sparsifying transform in some domain. This is denoted through the sparsifying matrix psi, which yields a sparse vector S. And by sparse, we mean that the L0 norm, which is the number of non-zero elements of this vector, is much smaller than its ambient dimension. Also, we have an observation matrix which effectively deletes the rows of psi such that we can observe y through this observation matrix phi. Now, multiplying these two matrices yields matrix A, which is called the sampling matrix. And there are several important properties associated with this matrix, specifically that it should have the null space property, and which means that it should be a vector x plugged through A should be uniquely identifiable, and the restricted isometry property, where again it means that A preserves the lengths of this associated vector x. So under relatively broad assumptions and with the appropriate construction of this matrix psi, we can actually solve the following problem. We have some records psi, which are observed through this matrix, and this is our sparse representation, our sparsifying transform. For a simple case, it could be like a Fourier matrix, and S is the sparse vector of coefficients. So now we solve this underdetermined system of equations to actually find this sparse coefficient vector S, and to hope to actually reconstruct the missing observations associated with Y. There are several strategies to perform this optimization efficiently. One standard approach would be to minimize the L0 norm, however, subject to this constraint. However, this is not sparsifying promoting enough, and it minimizes the energy of the signal. So ideally, we would like to minimize for the L0 norm, as I mentioned previously. However, this is an NP-hard problem beyond trivial cases. And typically, a very popular choice is to actually adopt a convex surrogate for this. So minimize effectively the L1 norm subject to this constraint. And L1 norm leads to a convex optimization problem, which is because the L1 norm is the tightest convex envelope of the L0 norm. Okay, the question now is though, what is an appropriate representation for the wind field data? The way we can think about this from a simulation perspective, at least, is go back to this wave number frequency formulation that we looked before. This is the original formula I introduced earlier, where these phi are the random angles. And by using some trigonometric identities and some mathematical manipulation, we can actually express this x in terms of a beta matrix, which is nothing else other than the tensor product of sines and cosines associated with the wave number and the frequency domain. And lambda now is the amplitude associated with the spectrum, and A now is the transformed through sines and cosines random phase angles. So now we have reinterpreted basically the spectral representation as nothing more than a Fourier matrix decomposition. So practically, in terms of 1D extrapolation, where we are observing the blue records here, and we wish to infer the full missing red records here, what we do is we use a tensor product of these bases, where it is important to note what we can introduce additional atoms to enhance the resolution, so more atoms than the standard Fourier representation dictates. We can do this to some degree. And then after the construction of these bases, we can concatenate them together with the associated records. And we can observe only the associated measurements by removing these extrapolation points effectively to actually find this sparse coefficient vector W by this large scale L1 minimization problem. I will not go into the details of how this was implemented. It was a bit cumbersome, but it is feasible actually to implement for cases up to as the ones I'm showing here. Okay, so if we do this, we can see, for example, that the whole missing time history here, which is reconstructed, it's pretty well preserved in terms of its temporal characteristics. We can observe the same thing for the power spectral density, the coherence function with another missing time history, and the correlation with another missing time history. With the exception that the power of the associated statistical quantities is a bit underestimated. This problem is exacerbated in general if we move to this computational memory overhead problem is exacerbated if we move to higher dimensional domains. So if we would be looking at a two-dimensional problem plus time, then this would require a very large sampling matrix due to the tensor product multiplication. And as I said before, this leads to a large-scale optimization procedure. Also, in many other cases, this restricted isometry property is not guaranteed because we are removing multiple rows from the matrix. And an appropriate basis is not known a priori. So in many cases, there's not a straightforward way to have an analytical expansion for real-world signals. And this Fourier assumption, for instance, can relies on stationarity and Gaussian assumptions. So in general, these limitations motivate, when we want to move to higher dimensional domains, a basis-free approach. So in this way, we resort to the concept of matrix completion. And the idea here is that an appropriate rearrangement of our data yields a low-rank matrix, where the low-rank property is interpreted as the generalization of sparsity for matrices. So in analogy to sparse vectors, a partially observed matrix can be reconstructed by the minimum rank matrix among all possible matrices that are consistent with the observations. Again, in analogy to L0 norm, the rank is NP hard to be minimized. And motivated by the success of the L1 norm, we adopt again a convex surrogate, which is the nuclear norm here, which is basically the sum of its singular values. A very standard procedure for solving this optimization problem relates to this singular value thresholding algorithm, where the idea is to apply, to have a minimization in the form of here, where we minimize a matrix of nuclear norm, denoted here, subject to this projection operator, which gives us only the observations of y in terms of m. So everything else outside of this observation set is effectively, we do not observe it. And the idea is to perform sequential updates by first thresholding the singular values of x, and then afterwards of y, I'm sorry, and then afterwards updating that in terms of the observations given by this expression over here. So the mechanization of this technique for the case of wind field data is that we are now considering a two-dimensional domain where the missing data are denoted by red. We can have up to 50% missing data, and we can try to minimize this standard problem. In reality, this singular value thresholding algorithm is relatively computationally slow to converge. So we adopt a relationship related to robust PCA. In particular, we minimize at each time instant of this domain the following optimization problem, where now I is the time component and epsilon is a corruption matrix. And we are only observing the values that are outside of this observation domain. And M are the actual observations. So by performing an augmented Lagrangian viewpoint of this, we are defining an objective function given here by L, where at each time instant, again, we have this nuclear norm. Lambda are the Lagrangian hyperparameters, and mu is a hyperparameter which is to be tuned. And this is the Frobenius norm of this error over here. The motivation behind this is that this augmented Lagrangian procedure actually has much faster convergence due to the introduction of this quadratic term. And the general solution of this, which I will skip the mathematics, but the idea is to solve a sequence of unconstrained optimization problems where the solution of the previous problem is used as an initial guess for the next one. So first, the Lagrangian is optimized with respect to y and e by proximal gradient steps, while keeping the Lagrange multiplier as fixed. And then the updated singular values of y are updated. The singular values of y are updated using software thresholding shrinkage operations, as denoted before. And then the lambda is updated based on the degree of the violation of the constraints. So if we do this for a missing time history, let's say here P2, we can see again that the whole missing time history is relatively well preserved. And again, in terms of power spectral density in normal and logarithmic coordinates, if we compare the target with the actual data and the extrapolated ones, which we have not measured, we have pretty good accuracy in terms of its power. And the same could be said about the coherence and the correlation function between two missing data points. Okay, so far we have presented a method for a 2D problem. However, this doesn't come without certain limitations. In particular, although it gives a convex optimization procedure, this low-rank assumption might be valid for simulation purposes, but over large domains where there's an extensive spatial variability, this is not necessarily a valid assumption. Also, this method solves independent optimization problems in terms of time, so it ignores the actual temporal correlation. So it misses out on information which is inherent in the signals, and it's ignored. Also, this lacks interpretability, despite the fact that it could be readily implemented on a real-time basis. It lacks interpretability. So having a basis that could be trained somewhere cannot be deployed somewhere else. And in general, we do not have an uncertainty quantification on the estimates. So ideally, we would like to have a method that learns a sparse representation from the data, and then to do this in an adaptive manner. So there is a field called dictionary learning, and this offers several algorithms for finding linearly independent sets of vectors together with their coefficients. And this can also be viewed from a Bayesian viewpoint, where the idea here is to find both A and W, given some data zeta, where here zeta are, let's say, the snapshots of the wind field. Of course, subject to some sparsity constraint for W. Although there is a rich body of work for this, the main limitation is that one, there is an assumption about the error distribution, and also the fact that it's not always straightforward to implement this. For instance, when we want to construct a basis on several points which we do not measure, it's practically infeasible. So ideally, we would like to have a more structured way of inferring the construction basis on points that we also do not observe. So in this way, we resort to a Bayesian non-parametric model, which this family of methods model the observations as a linear combination of infinite features whose number is not known a priori. So we basically try to adapt the model complexity as the data is coming in, and we try to infer the size of this model based on the data. And the size of this model, of course, could be infinitely dimensional. There is two motifs in this regard. The first one is the Dirichlet process, which has mutually exclusive clusters with each data point associated with a latent class. The second method is the Beta-Bernoulli approach, which is more general and models the process as a combination of latent features, where each feature is a Bernoulli random variable with hyperparameters sampled from a beta distribution. So this has been used for signal processing techniques and image processing, and we have employed and adapted this model for wind field extrapolation, and we actually have leveraged its UQ capability. So the schematic overview of how this works might look a bit complicated, but the main idea is that we perform a partitioning of the data. So we have this two-dimensional domain I showed before, and we take voxelized partitions, yi, which are observed through a matrix sigma I. And this y is assumed to have an expansion based on a dictionary which is fixed independent of the data. So this is the lower dimensional representation, and it's linearly expanded through some coefficients w. together with some observation error epsilon I. So the idea is to infer D and WI together with the statistics of the error. And to do this, actually, what we do is we impose several Bayesian priors on the models. The one relates to the columns of D, which are normally distributed with this diagonal covariance. W, which are the coefficients, are associated with the sparse coefficient weight, with a coefficient weight, which is given by this distribution. And the error here, which is given by this distribution where these hyperparameters are gamma distributed. The important thing here is zeta I, which is given by the following hierarchical Bayesian model, which its zeta I is given by this Bernoulli distribution, which is further hyperparameterized by this beta distribution. The main idea here is there is a strong mathematical justification of why one needs to do this. The main idea that this beta Bernoulli process defines a distribution over sparse binary matrices, which could be theoretically unbounded. And with increasing data points, as the data partitioning voxels are increasing, the number of new non-zero elements diminishes. So this essentially is the sparsity component. Also, when an atom is shared in one of the measurements, it is also more likely to be reused. So there is also, let's say, shared sparsity between the representations. And one of the most important things is, despite, on top of the fact that we have uncertainty estimates, we can also use Gibbs sampling updates to infer the full posterior, because all of the distribution of all of these, variables are actually complex conjugate. So this is what the full posterior looks like. And by conditioning on one variable based on the others, we can perform sequential updates as the data is coming in to find the underlying hyperparameters of all of these distributions. And we can do semi-analytical updates, which makes this much faster than compared to, let's say, Markov chain Monte Carlo or an approach like that. So schematically, I have omitted here, by the way, I have omitted the long list of update equations because I don't think it facilitates the presentation here, but please feel free to ask me about any questions you might have about that. So the mechanization again here is the same as before for the nuclear norm minimization, where we solve independently for time for this grid. But now for the non-parametric Bayesian dictionary learning technique, we have this, let's say, voxelized partitioning of the data, where we perform a vectorization of this voxel, and each of these vectorized, let's say, boxes is one YA data point, which informs this posterior update. And this is, in an overlapping manner, it's being slided to the right and lower in the same way as a convolutional method would use. And we have considered this application for 60% simulated data. And we compared these two methods. We can see straight for a point that is missing, we can see that the full time history is reconstructed with both methods, but with actually better detailed and with an uncertainty estimate in terms of this beta process factor analysis. And in terms of the power spectral density in logarithmic coordinates, we can see much better efficiency. And the same is seen for the correlation between two data points, which are both missing. The same applies for the probability density of an unknown point and also for the distribution of the error reconstruction. So we see here that the error of the BPFA is much lower and much more narrowly concentrated. Okay, so the last part of this talk is to showcase the applicability of this method in actually real-world data. These were collected through a series of studies which analyze non-Gaussian wind effects on structures, and were collected from the University of Florida boundary layer wind tunnel facility. These experiments involve wind blown on a rough channel by 8 vaniaxial fans, which are followed by configurable mechanical reference elements that generate boundary layer-like turbulence. And here we have measuring probes, and we have considered only the sides of the building. There is a small building here which is not shown. and we have 240 pressure taps, of which only 50% are considered to be measured, and we try to infer to the remaining ones. So we do this with both of the methods I described previously, and we can straight ahead see that the reconstruction of the wind pressure is much better using this beta process formulation. And the same applies with the power spectral density and also the probability density, which exhibits significant non-Gaussian characteristics. If we look at here the probability density, the distribution of the error, again, we have a similar behavior for this beta process factor analysis. And here we can also see that the Heilinger distance, so the distribution of this PDF reconstruction error, is much better for the beta process factor analysis. As a last metric, here we see the predictive variance of the Bayesian approach compared to the error, vis-a-vis with the error. And we can see that there is a qualitative correlation, which indicates that the predictive variance is well correlated with the error, indicating that this method could be used for a variety of scenarios in predictive modeling. As a future work, the idea now is to use this predictive variance as a sensor deployment strategy using active learning, or to employ more structured priors for constructing these dictionary atoms. So let's say that the columns of this expansion matrix D could be distributed through some sort of physics-informed or computational fluid dynamics-informed manner, such as the exponential decay function I showed earlier. So the contribution here is that we have extended the previous approaches to even 4D domains, 3D plus time. We have considerable degrees of missing data and actually real data with non-Gaussian characteristics. And we have UQ capabilities that actually could potentially lead to paradigm shift in computational modeling, but also for guiding the sensor deployment strategies in structural health monitoring applications. So that's it for me. Thank you very much for being here today, and I'll be happy to take your questions.
Thank you so much, George. It was a great talk. Are there any questions from the audience?
Hi, George. It is a great presentation, and you explain everything so clear to me. I want to ask you, using the BPFA method, what is the computational efficiencies of that compared to other methods?
Yeah. I have to say that I didn't mention that there is a computational burden of this method, because we have to perform updates with relatively considerable amounts of data. So this is, let's say, a 4x4 multiplied by the full missing time history. And for this boundary layer experiments, we were very high frequently sampled. There was a high computational cost. For example, I think if I remember correctly from the paper, this took 2.8 hours for multiple realizations. So this has been performed, I forgot to mention that, for multiple realizations of the stochastic process. So imagine this scenario multiple times. This took about 2.8 hours versus this one, which took 1.6. But the benefit of the fact that we have higher accuracy and we are have uncertainty estimates, for me it's more important.
And I have another question. Can we also implement some physics constraint inside this method?
For the beta process factor analysis?
Yes, like to
for this one.
Yes.
Yeah, it could be through some structured priors, for sure. That would be the most straightforward case. If there would be some additional constraints, such as adding a penalty loss, which is the violation of the physics or something like this, then I guess you would have to do a bit more mathematically involved formulation. I have not seen that in the literature so far. But yeah, if you have any idea after, we can discuss how that could look like.
Yes, thank you so much. I really enjoy your presentations. You explain everything so clear to me.
Thank you.
I was also wondering if your model is able to handle the measurement noise. Like I assume the vintage data is a bit noisy. Are you able to like separate your uncertainty resources in a model, or can this be included?
That's a very nice question. The data that I used were pre-processed, so I treated them as like the ground truth. Now, perhaps one could perform like a decomposition of this error to further distinguish it from, let's say, measurement error or modeling error or something like this. So I guess this would have an additional, more complex representation here. But yeah, this is a very good question. The error here now is the prediction error, basically. Oh, but actually no, it also incorporates noise. It's both. It's both, but it doesn't. The model does not distinguish.
Okay, thank you.
Yeah.
Are there any other questions? If not, I think you can always reach out to George about any questions you have. I just want to ask a couple general questions because your background is very diverse. You've been kind of all over. And coming from Europe, I just want to ask, what was the most challenging part in adjusting the research in the US in your experience?
Yeah. This is my personal, experience. So I'm not sure if it would be the most objective description of reality. I guess it was it. In my opinion, comparing the groups I was before and after, they both have their very good groups. But it was. I feel it's a bit more fast-paced in the US. Like the work ethic and people are usually all day at the lab and in many cases. There's more meetings, more deliverables. It's my sense that in Europe, things are a bit more relaxed. It's also the constraint that I guess in Europe, it's not mandatory to have like a master's the first year of the PhD. So having to also do a master's here also induces a burden, I think, in terms of studying and workload, which I think it's good to do that, to be honest, especially if you want to focus somewhere. Also in the US, I feel like that it's more PI driven in many cases, the projects, compared to like large consortiums and widespread funding initiatives like in Europe. And much of the funding here is motivated by ARL or labs like that, which I didn't notice that often in Europe. But you have the opportunity to do very cool projects. I don't know if that answers your question, but yeah.
No, I think it was great. Yeah, you were also you got a fellowship in Germany, so you can actually compare it really well. Do you have any advice for finding a postdoc position in the US?
Yeah, the main idea is to try to reach out as many people as possible, whoever you know, or even if you don't know, and ask if your professors know someone else, even if you don't think there's a high probability of that happening. A very well tailored email with outlining your contributions and explaining in a passionate way what you want to do. And of course, finding groups and people who are adjacent to your research agenda. Another idea is to, try to diversify your research profile. It's very unlikely that you're going to end up doing the same thing that you were doing before. So doing like something more data-driven or something in a different domain would be a very good way. Or even go there in person if you happen to visit that university for a conference or something. Going there in person or talking to the professor in person is always much more helpful, and they will remember you if you compare to doing that like in a just by email. Also reviewing papers, going to conferences if you can. Everything you can imagine you can do. Reaching out to people. Yeah, these are strategies I try to implement.
And lastly, do you have any advice for grad students in computational mechanics?
I'm more of a stochastic dynamics guy, so I would reserve to give like an advice on that. Always doing something
That also
data-driven.
works.
Anything else?
I think that's all. Thank you so much, George, for a wonderful presentation.
It was
And
a
we
pleasure.
also
Thank you for inviting me.
thank people who joined our seminar today. We are looking forward to see you next month. Thank you.
Thank you. Bye, guys.